Welcome back. So what we're doing today is introduction to functions. Last class or last lecture, I guess, what we're doing is the real numbers and the properties of the real numbers. So we have all these different properties, and now what we're going to do is use it to describe the functions of real numbers, and then we'll get into limits in the next chapter, and then derivatives will be defined using limits. So let's get to it. So what we're going to do is we're going to have a function. What is a function? A function, roughly speaking, is a rule. So the function is our definition here. We'll pictorially describe it, and then I already pre-drew the picture so that you can see what we're talking about, the domain and range. Domain is horizontal, you can think of, and range will be vertical, is how you can think of this. Is a rule which assigns to each x in a set A. This is our notation from last time, which is going to be here. This will be our domain A. It defines a unique value. Let's call it y equals f of x inside another set B called the range. So A is the domain, the vertical, or sorry, the horizontal. I said vertical as I did this. The horizontal is the domain, and then it sends it to B, which is the range, or image sometimes. So these are also the definitions. We can, of course, also do this pictorially. So we can have our set A and pick a point X in here. And then we can pick our point B. This is our range. And we need a point which is y equals f of x. So basically a function is moving points around is what we're doing. And then our function goes between these. And it assigns to each point x a unique point y equals f of x. All right. We'll get to the graph in a second, but that we take the horizontal and the vertical and put them together to get the graph. So let's look at a couple examples of functions. Basically, what we're going to do first is we're going to give the algebraic expression for a function, and that's what we're going to do with the first thing we're going to do is domains. So the algebraic expression is going to induce a domain of definition, we're going to call it. So, but first of all, if we say that f of x is the rule that sends you to x cubed, say, or we can have, say, g of x, because g comes after f. G of x equals, say, 1 over x, the reciprocal of x, which we can also write, you should get used to, as x minus 1. So what are these? We've now given a description of these, and what we're going to do is I picked one which has a domain of everything and one where we have to restrict. So first of all, when we want to start analyzing functions, the first thing you can do is plot points and try to sketch the graph, we're going to call it. So I'll just do it intuitively. If we have these, for each one of these, we're going to have an x value, which we're going to pick, and we're going to start thinking about which values we're allowed to take and which values we're not allowed to take. And then we can have f of x, say, and then g of x. We can plot them on the same one or on different ones. But what we're going to start seeing is you can just pick a bunch of different values. And then so let's go -1 or -2, -1, 0, 1, 2. Same thing here. We could do -2, -1, 0, 1, 2. And so for this function, it's a polynomial, which is a monic polynomial, so we can just keep going. So what we're going to do is this is going to be negative 2 cubed is the actual calculation, which will be negative 8. This one will be negative 1 cubed, which is negative 1. This is 0 cubed, which is 0. This is 1 cubed, which is 1. Negative 1 cubed, which is negative 2. Oops. Negative 2. Oh, I ruined it now. Negative 2 cubed. This is 1. And then 2 cubed is 8. So we start getting ordered pairs, we're going to start calling them from last class. This is why we need the Cartesian plane. And then so what we're going to get is at negative 2 we get negative 8. At negative 1 we get negative 1. At 0 we get 0. At 1 we get 1. And then at 2 we get 8. So we can start building what we're going to call the graph. And then this will start doing the first thing we're going to talk about, which is going to be domain. Let's look at the domain. Here we go negative 2, so we're going to get negative 1 over negative 2, or negative 1/2. Here we're going to get 1 over negative 1, which is negative 1. Here we get undefined. We can't divide by 0, so when x is 0, we don't have a value there. This is what one of our 2 mantras are going to be. The first mantra is don't have negatives under even nth roots. We'll talk about, so if you have square root of x, this means that x has to be greater than or equal to 0. This will be our first mantra of domains, because you can't have 2 negative numbers multiplied to give you a negative, and you can't take 2 positive numbers and give you a negative. So you have to have positives or non-negatives underneath even nth roots. And the second one is don't divide by 0. So this function is undefined at 0, and you can't draw a point on the graph for this function at that value. You can start plotting points. Next we get 1 over 1, which is 1. Here we get 1/2. So if we're going to start trying to plot these guys, color coding, cubed, we can do as green. What did we get at negative 1, 1, 1? Oh, no, I need 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I won't draw them on the same plot because this one will be slightly bigger or slightly smaller scale. So at negative 2, we got negative 8. Negative 1, we got negative 1, 0, 1, and then at 2, we got 8. So if we start plotting more and more, we're going to start getting a picture, which we're going to call the graph of the function, the graph of x cubed. And then in the next thing that we're going to do is we're going to draw the 1 over x guy in orange. So 0 has no value, so that means that this is basically what we're going to start calling a vertical asymptote. We're undefined at 0. And then if we start looking at this, negative 1/2 or negative 2 gave me negative 1/2. So here's 1, so right there. At negative 1, we got negative 1. And so if we start plotting a whole bunch of points, we'll get this. And then same thing here. At 1, we got 1. And then at 2, we got 1/2. And we'll start getting something, well, not going back up. So then it looks like this. So this is 1 over x. The goal right away in the next few videos or lectures are going to be to systematically look at and deal with the graph of functions and the standard functions. And then we'll use transformations to move them around in the plane. That's where we're going to go. But before we do that, let's do the domain of functions and then define what the graph of functions is for this lecture at least. But the moral of the story is, if you don't know what the graph looks like, plot a few points and you might get an idea of what it looks like. That's the first thing that we do, brute force. Just plot some points. Same for trigonometric functions and everything else. We use the unit circle to plot points, and we see that it's a wave. Definition. Given an algebraic expression for f of x, that says expression, for f of x, the domain of definition So that's what you're going to call the domain. We can restrict the domain and define a function on different sets eventually for convenience, etc. But for now, when you're given an algebraic expression, the domain of this thing is every point in the real numbers, which makes sense. So in R, from our notation, which make the expression f of x true or make sense. So all the permissible values you've probably seen at some point. Our mantras are going to be mantra 1. We can't have negatives under, I shouldn't write in green, mantra 1. So we can't have negatives under even nth roots. And I'll remind you even nth roots in a second. So what does that mean? If I have 2k, so n is an nth root, which even means it's divisible by 2. So if I have an nth root of some expression in x, my variable, my independent variable, no matter what it is, this immediately tells you that you have to figure out when is a of x greater than or equal to 0. And this is the first application of nonlinear inequalities, is trying to find out when this is greater than or equal to 0. As an example, if this was the square root of x squared minus 1, we immediately see that x squared minus 1 has to be greater than or equal to 0. What we do is we split it, like I showed you in the previous lectures. We split this into its linear terms and find out when that makes sense, and then that's what will make sense for your domain. Check this first. It will give you intervals. We'll do an example in a second, but check this first. It'll give you intervals, and then after we do that, we do mantra 2, which is don't divide by 0. And so what does that tell us? If you have some expression, say b of x over c of x, some quotient or ratio, or remember I wrote 1 over x as a negative exponent, so things that have negative exponents or have division is your red flag for this one. If you have something like that, that immediately tells you, I don't care if this is 0, that just means your function, this is your function. This will just tell you your function is 0. But if c of x is 0, that's bad. We have division by 0, so you have to immediately do this. And then, so what you're going to do in general for the functions that you're going to get is you have to check if you have an even nth root. If it does, you find out your intervals, which will make sense for your function. And then you're going to eliminate all the points in those intervals where you divide by 0. Let's do exactly that. Example, find the domain of, say, f of x equals, let's do 1 over, so you can see it there, and then the square root of x squared minus 1, the one I was just talking about. I did some of the work already. Let's find out what's going on. So we do have both bad scenarios, worst case scenario. Solution. First of all, I have an even nth root, x squared minus 1, so this tells me mantra 1. You can justify any of your implications, technically speaking. This tells me that I need x squared minus 1 to be greater than or equal to 0, because I can't have negatives under even nth roots. The next thing I do is it's nonlinear, so what we don't do for sure is write this as x squared is greater than or equal to 1, and then try to square root, and then say x is greater than or equal to 1. or something crazy like this, that you're going to miss a whole interval. So this is bad. Don't do that. Your tendency is going to be want to do that. But what we're going to do is we're going to rely on the previous video and use the application of solving nonlinear inequalities. What we do is, this is complicated, so we break it into its linear inequalities and then check all those ones and then find out when this is true. So instead, we factor this x minus 1, x plus 1 greater than or equal to 0. When does that happen? Let's check. I'm looking at the real number line like this. When is it equal to 0? At -1 and at 1. And now what we've got is axons or dendrites or the presynaptic cleft, potassium or sodium flooding in. We don't know. Everybody in these intervals is positive or negative. The only place they can switch values is at the gates. This is neurons, axon, dendrites, in between presynaptic clefts. You're allowed to be 0 or switch your potential at those gates, -1 and 1. Everybody else in between has to be all positive or all negative. The only place you can switch from positive or negative is right here and right here. So now all I have to do is check. I check my linear functions. I put the lowest root. So this gives me the root x equals -1, and this gives me the root x equals 1. Why? Because it's x minus minus 1, which is x plus 1. So I get x plus 1 here, x minus 1. The combination of them, x squared minus 1, is their product. And then I wanted greater than or equal to 0 is what I'm checking. Then what intervals do I have? I have, in interval notation, I have -infinity to -1, this one, -1 to 1, this interval, and then 1 to infinity, this interval. Now I'm going to check each of these individual linear pieces. Less than -1, so at -2, I just pick a representative in there because they're all going to have the same sign. At -2, -2 plus 1 is negative. So they're all negative. And that's bad. I didn't want that. Or sorry, that's not my conclusion yet. I only did one piece. But luckily, if I pick -2, -2 minus 1 is also negative. And then I'm going to do this because then we're going to multiply them together. Oh, almost got myself. -1 times -1, or the negatives, gives me a positive. So we're positive in that interval. So yes, we're going to keep it in the domain. In the next interval, what we have is in here, let's pick 0. 0 plus 1 is positive, but 0 minus 1 is negative. Positive times negative is negative. So everybody was negative, and we get no. And then in the last interval, what we're going to do is pick any representative, say 2 is in there. And then we look at 2 plus 1 is positive, 2 minus 1 is positive, positive times positive, positive, keep it. Everybody in there was positive. This is how I'm checking. So a potential domain is going to be -infinity to, and right now it's greater than or equal -1, square bracket, union, square bracket, 1 to infinity in notation. And now we're going to have to change those square brackets to round brackets and eliminate -1 and 1 because our function has division by 0 also. So that's the first step, is creating from the nonlinear inequality of the even nth root. You're going to turn it into intervals that you get and then just eliminate division by 0, which is much quicker. Just a second. So mantra 2 tells me that if I have 1 over the square root of x squared minus 1, x squared square root minus 1 can't equal 0. So square both sides. This tells me that x squared minus 1 can't equal 0, which means x squared can't equal 1, which means x can't equal plus or minus 1. And that tells me that the domain 1 over the square root of x squared minus 1 is equal to -infinity, -1 round bracket, union 1 infinity. Let's stop there and we'll do another video about domains.